In Practical 3, we worked with complex digital circuits such as demultiplexers, counters, and clocks. The demultiplexer can select a single output from many possible ones, using a combination of the select line inputs. Our demultiplexer had 4 select lines, A3 through A0, which allowed for 16 possible outputs. Our circuit only had 8 LEDs, so the operation had to be done for 2 cases, one for when A3 was 0 and the other for when A3 was 1. For the first truth table, we looked at the first case, when the select line had 0 for A3. This showed the LEDs light up from 1 through 8 for binary inputs 0 through 7, where A3 is the most significant bit and A0 is the least significant bit. For example, 0101 would light the 6th LED and have a binary value of 5. For the second truth table, we looked at the other case when the select line had 1 for A3. Again, the LEDs lit up from 1 through 8, but now it was for binary inputs 8 through 15.
In part 2, we built a circuit featuring a 555 timer clock and counter leading to a 7-segment display. The IC generated clock pulses that passed to a 4-bit counter driving the display. Each time a capacitor was changed, the frequency changed. This is because the charge and discharge time of the capacitor is dependent on the resistance and capacitance. The frequency of the 555 timer can be determined with this equation, which shows that for a larger capacitor the frequency will be lower. The 100 nanofarad capacitor produced such high frequency that the display didn't switch numbers but had all the segments lit up at the same time, showing a constant 8. When we connect pin 2 to a push button, the clock is inhibited. When pin 15 is connected to the push button, the counter resets.
In part 3, we created a shift register, which is a cascade of flip-flops with a common clock, with each flip-flop feeding their output to the next one's input, shifting the memory 1 bit each clock cycle. Our shift register had a push button to set the first bit. When we connected the circuit, it did not work correctly, because for each clock cycle, we would get 2 pulses as if 2 cycles had happened. We found that the rising edge of the 555 clock signal was noisy. Our solution was to feed the clock through a SR latch debouncer to clean the clock output before feeding it to the D flip-flops. When the button is pushed very quickly, nothing happens. This is because the push button and the rising edge of the clock have to meet at the same time. For every combination of button pushing, we got the output shifting 1 bit at a time, which is the expected function.
In Practical 4, we constructed a PBG circuit. Few concepts to keep in mind are filters, active and passive, or high or low, cardiac poles, digital displays, reflective optical sensors, and signal amplifying. How does the sensor sense our pulse? Infrared light is emitted and hits the surface of our finger. Inside the finger, it lands on deoxygenated hemoglobin, which then scatters off and out of the finger and into a detector. The pulse is defined by the variation of blood volume in the skin due to the pressure pulse. In this exercise, we built a circuit that filters this infrared light and uses the AC component peaks to light up an LED or a diode. So when the LED light flickers, it indicates a pulse, or the AC peaks. 2 types of filters were constructed to filter and amplify the V-sensor output. One passive high-pass filter and non-amplifying, and one active low-pass filter and amplifying. For the high-pass, we chose a cutoff frequency of 0.7 Hz, so frequency higher than that will pass. and use this equation to find which resistor and capacitor to use. For the active low-pass filter, we choose a cutoff frequency of
2.3.
so low frequency will pass, and signal gain amplifying of 101. These are the equations we use to find which parts to use. After that, we amplified the low signal once more, with another round of the same filter route. Same parts were used for this route, adding to a total of 10,201 times the amplification. Then each group member tested the PPG.
For the second part, we redid the 7-segment display counter from Practical 3, but this time it was driven by our PPG. Later, we fed the carry-out from the first counter to another counter to display 2-digit numbers. This led to us being able to count the heartbeat for each group member and easily calculate their pulse. To make sure that our device was sensitive to heart rate changes, we did measurements for each group member's resting heart rate and the heart rate after intense exercising.
Thank you for watching. Please like and subscribe.